Previously, we have seen that in case of hydrogen atom, for example, an electron can absorb energy and go to the higher level, or it can emit energy and go to the lower level. Um, Similarly, in case of molecules which is more than one atom can also absorb or emit energy by changing the configuration of their electrons, just like atoms. In addition, molecules can also absorb and emit energy of much smaller quantities by some other ways. For example, one way is atom in a molecule vibrate about their equilibrium position, just like mass on a spring. And another way is atoms rotate about the center of mass of a molecule. Now, such vibrational and rotational energies are often unique to a particular molecule, and that's why it can be served as a fingerprint in identifying a simple molecule. So let's look at how do these energies are comparable to each other and also to the electronic transition energies. Okay, let's remind us again. Molecular energy states arise from first is the change in its electronic configuration, just like atoms. Molecular electronic states have highest energies, typically separated by several electron volts. And the spectra is usually in visible and UV region. As I explained before, molecular energy states can also arise from vibration of its atoms about their equilibrium positions. Vibrational states are separated by around energy interval of 0.1 electron volt, and you can calculate for energy states separated by approximately this electron volt of energy. The spectra will be in IR region. Rotation of atoms about the center of mass of a molecule also gives rise to additional molecular energy states. Rotational states of a molecule are separated by very small energy intervals of the order of 10 to the power minus 3 electron volt. And thus the spectra that arise from transitions within rotational states fall in microwave region. So in this way we can see that the energies or the spectra arise from an electronic configuration or vibrational or rotational are in completely different energy regions, completely different wavelength regions. In order to find out what are the vibrational energy states, let's first look at vibration of atoms in a molecule or vibrations in quantum mechanics. Atoms in a molecule vibrate about their equilibrium position just like a mass on the spring. And we have seen that kind of motion as simple harmonic oscillator motion, and how the energies of a simple harmonic oscillators are. We have seen that in a previous chapter on quantum mechanics in chapter 5. And such quantum oscillator has only certain allowed energy values. An allowed energy can also be written in terms of frequency. Here the allowed values of n is 0, 1, 2, 3 and so on. And ground state energy that corresponds to n equals to 0 will thus be half hf. And important point to remember from previous chapter is that the energy levels in case of a simple harmonic oscillator were equally spaced with energy difference of h cross omega. So one thing to remember, in case of one-dimensional quantum oscillator, 0 point energy is half HF, which is the ground state energy, and all the other excited energy states are very much equally spaced, and the difference between them is H cross omega or HF. And such an oscillator can emit electromagnetic radiation when the electron jumps from any higher state to a lower state. Now the thing is, there is also a selection rule here. Selection rule is that the delta n value can only be plus or minus 1. So only such transitions are allowed for which n changes by plus or a minus 1. So it is not possible to have transitions from n equals to, let's say here n equals is 0, here it's 1, 2 and 3. So transition from 3 to 1, for example, is not allowed. Transition can take place from 2 to 1 or 3 to 2 or 1 to 0 or 0 to 1, 1 to 2 and so on. So energy, so delta n can only change by plus or a minus 1, and this is vibrational selection rule. Now this model of quantum oscillator is oversimplified. In a molecule, the individual atoms can vibrate relative to the center of mass, because a molecule meaning more than one atom. So atoms can be of same mass, atoms can be of different mass, but the vibration of individual atoms is relative to the center of mass. That's why center of mass is important in case of a molecule. Another point to note down is that in a solid, atoms can often behave like a three-dimensional oscillator, and the properties of which will be different from the one-dimensional oscillator model that we are considering here. We'll discuss the three-dimensional solid later on in next chapter, but let's look at a vibrating diatomic molecule. Diatomic means a molecule which has two atoms of different masses. We are only considering here diatomic molecule because if a molecule has more than two atoms, the vibration of molecules can be in many different ways. So here we are only considering a diatomic molecule for simplicity. Let's say there is a molecule with atom of mass m1 and atom of mass m2 lying in an x-axis, and these rotate about their equilibrium position so that the center of mass remains fixed. Now, in order to calculate the frequencies of emitted transition, we must know the mass m and also force constant k, because it's like vibration is like mass on a spring, so we need that force constant k. Because now both of these molecules participate in vibration, we don't take these masses individually, but we need to take a reduced mass. Let's say if these two masses both vibrate about the equilibrium position, then they will have a total energy which will be simply the addition of kinetic energy of 1 plus kinetic energy of 2. And this total energy can also be written in terms of momentum. But now, in a frame of reference in which center of mass of the molecule is fixed, total momentum will be 0. So that your P1 is equal to P2. And thus the energy can be written as, we can take P1 and P2 as just P. So we can write it as half P square and then 1 over M1 plus 1 over M2, which we can reduce to p square by 2m, where m is actually the reduced mass, which is m1 m2 over m1 plus m2. So here Et equals to p square by 2m is the energy of the system, as if it were a single mass m here moving with momentum p. Now we will use this mass m in calculating the vibrational frequencies. Now in a diatomic molecule like H2, N2, O2, the masses of the two atoms can be equal. In that case, m value will simply be m1 by 2. For now, let's keep it the way it is right now, that if two masses are different. Now in order to find vibrational frequencies, we must know the constant K. Now in case of a diatomic molecule, let's say with a covalent bond, we have seen this kind of graph of energy as a function of distance between the two atoms or two nuclei. We see that when it forms a stable molecule, we get this energy minima in this kind of a curve. And at this minimum energy, the distance between the two atoms we call as R equivalent. So R equivalent is the distance between two protons, let's say, and that we call it internuclear distance. So R equivalent is the internuclear distance. So this internuclear distance is also like an equilibrium separation. And now in case of vibrational motion, molecule will behave like a simple harmonic oscillator in the vicinity of this internuclear distance. So, and we fit a parabolic oscillator potential energy U equals to half kx square to the molecular energy in that region. So in this figure, I'm showing the region of energy minimum here, and also a parabola that kind of approximates the curve near this energy minimum. And the equation of the parabola is, so here constant K can be determined by finding the value of R minus R equivalent that is necessary for a certain value of E minus E minimum. So with this, I would definitely encourage you to look at example 9.3 in the textbook, in which the vibrational frequency and photon energy of hydrogen molecule H2 is calculated looking at a graph for hydrogen atom. So definitely look at that example and see how it can be calculated. Okay, so instead of doing that particular example which is already in the textbook, let's say you have the K value for such an oscillator, simple harmonic oscillator with a two-body oscillator, okay, and the frequency of oscillation is 1 over 2 pi square root K over m. Here important to note down is m is the reduced mass. So this equation is, for example, for suppose you have m1 and m2, two masses vibrating about an equilibrium position, and the spring has a constant K. So this situation is equivalent to, suppose you have only one mass of mass m, which is our equivalent, which is our reduced mass, and this is vibrating and about its equilibrium position with spring with constant K. So when we have already reduced it to just one mass, then energy of such an oscillator can be given by this equation. Here, just remember this m is actually reduced mass. The allowed values of n can be 0, 1, 2, 3 and so on. And here n is called as vibrational quantum number. And again, remembering the selection rule is that delta n can change by only plus or a minus 1. So if we again draw the potential energy curve for a diatomic molecule, we see that inside this electronic energy states, you have vibrational energy states equally spaced. So these are the red lines are showing the vibrational energy levels. So vibrational energy levels are equally spaced. Now in case of hydrogen molecule H2, we see that the mass of one hydrogen and another hydrogen are same. So reduced mass will simply be half of the mass of hydrogen atom, and that's why F naught, which is half square root k by this reduced mass, will be 1.3 into 10 to the power 14 Hertz, and corresponding photon energy will be HF, which is 0.54 electron volt, and corresponding wavelength will be 2.3 micrometer. And you can see that this energy is in infrared region. So molecular vibrations typically give photons in infrared region. Now let's look at molecular rotations. So as I told you earlier, the second way a molecule can absorb or emit energy is through rotations about its center of mass. Now rotational motion is described by its angular momentum. We can imagine a rotor to be a particle of mass m rotating on the end of a massless rod of length r. But in quantum mechanics, it is not possible to have rotations in a fixed plane. Therefore, such a rotator cannot be a correct visualization of rotations in a molecule. A rotor in a molecule is described as a particle confined to move in all 3D dimension on a sphere of radius r. So for a diatomic molecule, let's say you have two masses of mass m1 and m2, and let's say the distance between them is between the masses and center of mass is x1 and x2. Now reduced mass will again be just like we defined earlier, m1 m2 divided by m1 plus m2. Since the origin of coordinate system is at center of mass of the molecule, then from the definition of center of mass, here m1 x1 will be equal to m2 x2. The rotational inertia of the molecule is I equals to m1 x1 square plus m2 x2 square. And we can also write this in terms of the reduced mass. And we also note that the equilibrium distance between the two atoms is x1 plus x2, which is basically the distance between the two atoms. So this rotational inertia of the molecule can be written as m r equivalent square. And the energies of such a rotational states can be given by equation. Here L is the angular momentum, which is I omega. Energy of a rotating molecule, how did we get this equation? So once we know the angular momentum, I omega, energy of a rotating molecule, which is basically the rotational kinetic energy, is given by half I omega square. Now what are the values of? It can also be written in terms of L square divided by 2I using this equation L equals to I omega. Now possible values of magnitude of angular momentum is given by this equation. Here we have seen that previously, and once you substitute this value of L in here, you get this energy of rotational molecule, and which is finally given by here. Now this energy, rotational energy, can also be written as B L plus 1. Here B is called a rotational parameter. So we get our equation for rotational energy states, which is equal to BL L plus 1. And of course, for any transition to occur, it should have a selection rule, and selection rule is the change in L value can be either plus or a minus 1. And these are for molecular rotations. Now we see that emission or absorption must follow delta L equal to plus or minus 1. So energy of emitted photon is the energy difference between two adjacent rotational levels. Let's just say there are two energy levels, one for energy with the angular momentum L plus 1 and another for angular momentum L. So for any transition between these two levels to occur, change in energy would be, so change in energy will be 2B L plus 1. That means energy photons have energies separated by 2B amount. So energies will be 2B, 4B, 6B and so on. And once we know energy, we can find out the frequency of emitted or absorbed photon. We know that the frequency of emitted photon is related to the change in energy when the transition is taking place, and that's why F frequency can be written as change in energy divided by H. So we saw that change in energy is actually 2B L plus 1. So frequency will be 2B L plus 1 divided by H. And since we know by definition B is H cross square by 2I, so frequency can be written as, frequency becomes L plus 1 H cross divided by 2 pi I. And we already know the relation between frequency and wavelength, which is C equals to F lambda. And that's why once you know the frequency of emitted or absorbed photon, you can also calculate the wavelength of emitted or absorbed photon in case of rotational motion of a molecule. Okay, so if we have to now draw the energy levels for because of rotational motion of a molecule, we see that the energy levels corresponding to rotational motion are not equally spaced. In the beginning, the separation is small, and as we increase the value of L, the separation between the energy levels increase. And we know that energy levels are given by this equation BL L plus 1. So possible values of L can be 0, 1, 2 and so on. Lowest value is 0. So for that, energy EL will be 0. So so here for the ground state rotational energy level, E value is actually 0. And as you increase L, according to this equation, energy will change. So if I have to draw the rotational spectrum, because L value can only change by plus or minus 1, for example, transition can take place from L equals to 0 to 1 or 1 to 2 or 2 to 3 or 3 to 4, and corresponding rotational spectra, you will get lines as a function of, let's say, frequency. Again, here I would encourage you to do two examples given in the textbook. One is example 9.4 to calculate the energies and wavelengths of radiations emitted by H2 molecule, and other is example 9.5. Let's look at another example here. So question is, if in carbon monoxide the L equals to 0 to L equals to 1 absorption line occurs at frequency of 1.15 into 10 by 11 Hz, what is the bond length of carbon monoxide molecule? Bond length is R equivalent, or the distance between the two protons. So in order to solve this problem, we know that transition is taking place from L equals to 0 to L equals to 1, but so we can find the change in energy. But before that, let's find out the moment of inertia of such a molecule. So this is the equation for moment of inertia for a carbon monoxide molecule. We can calculate now. Reduced mass of carbon monoxide is can also be calculated using the masses of carbon and oxygen, and that is 1.14 into 10 to the power minus 26 kgs. So once we know moment of inertia, once we know mass, we know that I equals to mr square. So R equivalent in this case will be simply square root of I over m. And when we substitute, we get the value of bond length as this many meters, or 0.113 nanometers. So just overlooking what we have seen so far, depending on their properties, some molecules may show purely vibrational structure with vibrational energy levels equally spaced, and with selection rule that change in n value can be the plus or minus 1. A molecule can also have purely rotational structure, and the energy levels corresponding to rotational motion are not equally spaced, and these satisfy selection rule delta L equals to plus or minus 1. However, in many molecules, the transitions between the levels must simultaneously satisfy both these conditions, delta L equals to plus minus 1 and delta L equals to plus minus 1. So in order to see molecular spectra, let's look at molecular electronic ground state, which is given by the bottom curve, and electronic excited state, which is given by the top curve shown with black line. Now we have, in addition to electronic state, we have vibrational levels also, and these vibrational levels, remember, are equally spaced. And within these vibrational levels, you also have rotational states, shown something like that. And just remember, the rotational energy levels are not equally spaced. Here I am showing the much cleaner view of such. So we have electronic states, then vibrational states, and within these vibrational states we have rotational states. Here zoomed version shows you that the rotational states are not equally spaced. So far we have discussed only vibrational rotation structure individually. What about if the transition is taking place within rotational and vibrational energy levels. Energy of the state with quantum numbers n and l can be written as allowed values of n and l are 0, 1, 2 and so on. Just to mention that this energy equation with rotational vibrational energies together is important equation. In the equation of energy that we just saw, vibrational term is usually much larger than the rotational term. And also remember the figure that we draw for vibrational and rotational energy levels. We saw that the vibrational energy level, the separation was much larger compared to the separation between the rotational energy levels, and that makes sense that vibrational term will be much larger, like vibrational energy term will be much larger. Therefore, in case of emission spectra, wavelengths usually correspond to n transition from n to n minus 1, with L changing from L to L plus 1. Here the vibrational transition is major contribution. So in vibrational, quantum number n will have to reduce n going to n minus 1. However, because the rotational term is smaller, that's why in case of rotational quantum number or L can change to either L plus 1 or L minus 1, because here vibrational term will lead to major contribution to the wavelength. In absorption, wavelengths will be those for transitions in which n increases by 1 unit and goes to n plus 1. So let's look at an example. Let's say a state with n and l value is transitioning to a state, or a molecule with n and l state is transitioning to a state where n is vibrational quantum number is n plus 1 and rotational quantum number is l plus minus 1. So possible absorption photon energies can be written as, here important to know it is for absorption. Absorption means it is going from lower energy state to higher energy state. I mean lower n value to a higher n value, and that is why change in energy is higher energy term minus the lower energy term. Now in a couple of slides ago we had the energy values for a NL state, and if I substitute those values, we can get. Now it's very important to understand this equation, okay? How did we get this value? So please make sure you review the equation and how we substituted n plus 1, L plus minus and so on. So notice that because it was not defined what is the final L value, it is still L plus or a minus 1 here in the equation. So for that we have two possibilities. One possibility is that L can go from L to L plus 1. In that case, delta E value will be HF plus 2B L plus 1. Other possibility is that L can go to L minus 1 level. Okay. Important is the transition between n and n plus 1 for absorption. Okay, so L value can change from L to L minus as well. So in that particular case, change in energy would be HF minus 2BL. So we see that for a same n transition, there can be two possible L transitions, and for those, separation between the energies or change in energy are different. So it's very, very important to draw the diagram for such energies and see how these values differ. It's really important. So let me draw that. So it is the expected spectrum of absorption photons. Okay, so now let's look at this very, very carefully. Starting from the center that corresponds to here HF, if you start from the center and increase to the right, it's a series of photons whose energies are given by, first, if the transition is going from L equals to 0 to L equals to 1, the transition would be HF plus 2B. And the next one will be HF plus 4B and then HF plus 6B. Important to note is the separation between them will always remain 2B, and that is the property of a rotational spectra, that the distance between the two lines is always 2B. Okay, so on the right hand side we have HF minus 2B, HF plus 4B and HF 6B and so on. And in the left hand side, when you go towards the left hand side of edges, we have a series of photons whose energies are given by HF minus 2B, HF minus 4B, HF minus 6B and so on. So the separation still remains the same, 2B. Okay, and it is very, very important for you to find out why L equals to 0 to L equals to 1 transition leads to energy of HF minus 2B, and it's because of the equation we just saw. And if the transition is taking place from L equals to 1 to L equals to 2, it is HF minus 4B and so on. And similarly, if transition is taking place to lower level, L equals to 1 to L equals to 0 or 2 to 1 or 3 to 2, there will be additional peaks in the left hand side of this HF photon energy. One important point, extremely important point to note is there is no line here at energy HF. So photon of energy HF is missing at the center of the spectrum. Such a photon would have corresponded to a pure vibrational transition, which will violate the rotational selection rule, and that's why it is missing here. So this is the ideal spectrum that you expect in that kind of transition which we just explained before. Now, what is the real spectrum that you get in a typical molecule? For example, hydrochloride. Let's look at the real spectra that we get from a diatomic molecule. Now this spectrum shows the absorption transitions of molecule hydro HCl here. Although the basic structure remains same, right? Whatever the standard shows, it has something HF, it has a center location where the transition is missing, and then you have equally spaced lines in the right hand side and then left hand side also something. But one thing to notice is there are very small number of differences. Okay, one is the transitions are not absolutely 100% equally spaced, and we expect the transitions to be separated by constant energy, but it actually, the distance decreases as we go away from the center position. And it is because first of all, we just when we calculated the energies, we assume that the molecule is a rigid structure with a constant rotational inertia. Okay, but in reality that could be different, and that is why you see the difference. Anyway, the idea is not to concentrate too much upon how the real spectrum looks like, the ideal structure. Important is to look at how the overall picture looks like. You have some central energy, vibration energy, which is missing, and then for L to L plus 1 transitions, you get energy levels in the right hand side, and these separation should ideally be 2b. And for L to L minus 1 transitions, you have energy in the left hand side of HF, and these are also equally spaced 2b. Okay, so this is molecular spectra of absorption spectra. Another thing to note is that L transitions from L to L plus 1 actually are all this energies are called as R branch in the spectrum. This is called the R branch, and in the left hand side where that corresponds to transitions from L to L minus 1, it's actually called P branch of the spectrum. So in a numerical problem, I may ask you to calculate the transitions or energy levels of R branch or P branch. You should know R branch corresponds to transitions from L to L plus 1, and P branch corresponds to transitions from L to L minus 1. Also, it is extremely important to just remember we did not consider the transitions taking place from one electronic state to another electronic state. Remember we shown you the ground electronic state and excited electronic state, because that will make life a little bit more complicated. But here what we have shown you is the transitions between two rotational and vibrational levels of the same electronic state, and that is why in the formula we did not consider the energy level of electronic state, because it's remaining same, so it will not make a contribution to change in energy. Okay, and these transitions in which two rotational or transitions between two rotational and vibrational levels of the same electronic states are called as rotational vibrational transitions, and these generally fall in near to mid infrared spectral regions. However, if the transition is purely rotational, as we have seen earlier, then it's called pure rotational transition, which falls in far infrared region, and so on. We have seen pure vibrational and pure rotational states, and this is rotational vibrational spectra. I also encourage you to look at example 9.6 of the textbook, in which from the absorption of HCl molecule, you have to determine the vibrational force constant and also determine the rotational energy spacing, which is actually 2b. Okay, so in order to first find the vibrational force constant, you have to first find frequency. Okay, and for HCl you can find the reduced mass, and from there you can calculate the K value, which is 4 pi square mf square, and that is your vibrational force constant. And then you find 2b because you have a formula, it's equal to h square divided by m r equivalent square, and you can get this 2b value. And this is very in good excellent agreement with the value estimated from the spectrum. Okay, with this I finished chapter 9 on molecular structure, and in next class I will entertain any questions from these topics. Otherwise I will start chapter 10.